We're going to go over the calendar in just a second, but 4.1 Part B has its own separate homework, but if you notice, it probably will be a bit shorter than 4.1 Part A homework. We do have a quick integration quiz tomorrow, like I just showed. Three different problems. Show me your work, rewrite it, work carefully. No, I will not give you formulas. Don't forget to see that your answer is complete. What do I mean? Write the plus C. There doesn't need to be, because it could be plus and negative number. Does that make sense? So in plus C, you have the option of positives or negatives.
So we can write.
Huh?
So we can write.
Technically. Because you're just trying to be unique. If it was logarithmic, maybe, but not with normal addition. No. Good idea. Okay. Hopefully you guys have your notes ready to go. But first of all, let's go ahead and quickly peek at our calendar. This isn't you guys. Hold on. Let me get rid of Algebra 1. Boop. Let me get AB. So are we on track today starting 4.1b, motion with integration? Yes. What are you guys doing tomorrow? And nice thing is I'll be here for period 1, so I'll tape it and I'll put it online. You guys help out the sub. Just go to your class folder underneath chapter 4 lectures. Sound good? Okay. Underneath class notes, all you gotta do is just get on the computer and open it up. I'll have it saved online. But anyway, section 4.1b, motion with integration. I'm going to go ahead and record us finishing this tomorrow. Due on Friday. False. This is not due on Friday. Guess when this is due? On Tuesday. Why? Because in class on Friday, are you starting a new section? No. In class on Friday instead, this is going to be a little annoying. Hold on. That's going to go, uh-oh. We'll figure out something. Who's an ASB on, oh, Ryan Murphy is. Anybody else? Angela is. Anybody else? I think that's it. Well, I'm going to have to fix your calendar because right now the test is here, so to move everything today is going to go on the ASB Disneyland trip. Does student council go on that as well?
I don't think so.
I don't think so either.
It's just ASB.
Oh, but I have 2 days for chapter 4A test review? Maybe I'll just delete that. No, we'll just do that. Anyway, okay, sorry, I'm changing your schedule as we're just sitting here. But long story short, in class on Friday is going to be a work day on 2 things. What's due on Monday? Or Tuesday? Homework from the book. And what else?
The motion packet.
Okay, now it's not going to be the entire motion packet before you. We are going to be doing some of it in class together, a little bit today and then a little bit more tomorrow. But whatever portion I tell you to finish for Tuesday is the portion that is due. Does that make sense? Okay. So make sure you're paying attention with that. And yes, once again, we are doing some of this in class. So that's due on Tuesday. That's going to go there. And in here, we're going to have in class work day on 4.1b homework and motion packet. All right, you guys going to work together on Friday? Yes, I'm just saying like, hey, be good for the sub and get stuff done. Sound good? I don't honestly know. Probably Brache. Okay, here we go. 4.1b motion. Have we talked about motion this year? Yes, we have. We even had 1 or 2 forever cards on it. Someone tell me something to do with motion from your forevers. Chris, go.
Velocity.
What about velocity?
You have to find the first derivative
Of the original function, who is? Position. We have x of t, who's position, right?
also acceleration.
From position, we have a velocity, and we have an acceleration. But how do you find velocity? Chris already said x prime of t, right? Thank you. How do you find acceleration? double prime of position, which is the exact same thing as, yeah, the first derivative of velocity. So we have position, we have velocity, and we have acceleration. We also have this other guy who's just kind of chilling. Speed, do you remember him? Yeah, your speedometer only has positives, not negatives, right? Because it just says how fast, not in what direction. Velocity is kind of like a vector with magnitude and direction. Speed is just how fast. Keep going back to the stick with me. You guys just kind of laugh. And then the prawn again. Oh yeah. Okay, so is there anything else we talked about with motion? If I put one word, maybe you'll figure out the other one I'm still waiting for. Yeah, I'm putting instantaneous because any velocity that comes from a derivative is instantaneous velocity. Question though, what's the other type? Average velocity. Right? And how do you find average velocity? And hold on, wait. Average velocity is always over a time interval A to B. What's the formula? Okay, it could be S of B minus S of A all over B minus A. Why am I using X just specifically on this page? Yeah, because I used X as my beginning position function. However, if I used S, then I would use an S instead. Anything else? Did we talk about, I don't know, different clues in motion problems like hit the ground? No, we didn't talk about that? Okay, then never mind. We'll talk some about it today. Alright, with that, that's some of the review stuff from earlier in our Forever cards, the motion formulas. However, let's use something else to help us review as well. And that something else is the worksheet. Kiddos, where does the worksheet start? The very first spot where there is no. Did you read the worksheet?
Yeah.
There's a blank space for a reason, because at the very top they're asking us for what are three closely related concepts upon which motion is kind of based? Oh my goodness, we just answered them. Position, velocity, and acceleration, yeah?
Yeah.
Good thing is, those are in our forever, so hopefully those are three things we can kind of keep straight. Now we can go ahead and go down to initially. Now guys, we could give more information like how velocity is the first derivative of position. Unless it's average, then there's a formula for it. But we already have that in our notes, right? So now we have some clue words to figure out, like initially. Someone give me a synonym or another way of saying initially. Don't tell me, fill in the blank, what it should be. At the beginning! At the beginning, what would equal 0 at the beginning? Time. Time equals 0. Don't worry, it's coming. There it is. Time equals 0. At the origin, this is specifically talking about, yep, position. Graphs where we're, or motion where we're talking about something moving along the x-axis or the y-axis, like an xy plane. That's not the only type of position or motion, I should say. But it is one type. The position is 0 is when they're talking about at the origin. What's another way of thinking about at the origin? Initial position, right? Initial position. At rest. What's going on there? Velocity. Why is velocity 0? You're not moving. If you're not moving, are you having a speed? No. At rest means you're stopped. Maybe only for a moment, only for a split second, but you're still stopped. So velocity is 0. You guys keep filling in. Number 4, velocity is positive, then the particle is moving to the, ooh, look at you guys. Correct? Because think about the xy axis, right? Where are the positive x's? On the right. Where are the negative x's? On the left, etc. So yeah, The right, but I'm also going to put an or, because not every motion or not every type of motion that we're dealing with is right-left motion. What if we were dealing with up-down motion? What would positive velocity indicate? Good, we're moving up. What would be the blank for number 5? The particle is moving to the left when the velocity is negative. So the sign of the velocity indicates the direction of the motion. Does that make sense? The sign of the velocity indicates the direction of the motion. What does the number of the velocity indicate? The speed, right? How fast? How fast in that direction? So could you be going negative 32 miles per hour? Yes. So you're going pretty quickly in the left direction, right? At least pretty quickly if you're not in a car and moving at that speed. That'd be weird. Okay, number 5. Nope, 6. Define average velocity over a time interval. Divide the change in good position by the change in time, which was the formula that we just wrote down a second ago. X of b minus x of a all over b minus a, right? Number 7 is true. It's not really a true or false question. There just isn't a blank for whatever reason. Instantaneous velocity is the velocity at a single instant. But how do we find it? Good. Instantaneous velocity, just a quick reminder, is the derivative of position. We already talked about it, but now we're writing it. Instantaneous, how do you find instantaneous? Derive. Number 8, if the acceleration is positive. Ooh. Did you guys hear what Kyle said? Go louder. If the acceleration is positive, then? Yeah, why is velocity increasing? Wait, increasing, decreasing tests. If the derivative is positive, then the original is increasing. Who is acceleration the derivative of? Velocity. Hence why we fill in velocity for the increasing blank. So number 9, if the acceleration is what, will the velocity be decreasing? So kiddos, these last few, aren't they really just applications of the increasing decreasing test? Cool. Number 10. Based on, more specifically, numbers 4 and 5, if you want to take a quick second, look at number 4 and 5. How would you answer number 10 for what needs to be true for the particle to change direction? Slopes? Generally, yes, but I'd like it a little more specific. Which slopes? Velocity values. The velocity. The slopes of position, which would be the velocity, will change signs. Why? Well, because we can tell up here, if velocity is positive, then the particle is moving to the right. If velocity is negative, then the particle is moving to the left, etc. Well, if that's true, then the only way to change direction is if the velocity changes signs. Now, you guys technically have a number 11, but for our purposes for today, we're going to kind of skip number 11, but let's go ahead and peek at the examples that come next. Let's peek at the examples that come next. Go to worksheet number 2, example number 1. Ooh, how many examples are there? Can you guys tell? Example number 1, example number 2, and example number 3. Now, there's more stuff after that, yes. But for the initial, there are 3 different examples. We're just going to look at them really quick, meaning, let's just analyze what's been given to you. Kiddos, how is the information given to you in example number 1? In a table, numerically. How has the information been given to you in number 2? Graphically. How about number 3? Analytically, or I would probably say, anybody know? Not numberly, that's true. Algebraically, yes, algebraically. Now hold on. In number 3, what function were we given? X of t. In number 2, what graph were we given? The graph of whom? V of t. Wait, and who is v? The derivative of position. Oh my goodness, so we were given the graph of a derivative? Have we done that before? Yes, we have. We're going to have to use those skills, like maybe look at the intercepts for the critical numbers. Then ask ourselves the question above or below after. Maybe make a little sign chart and think about above and below, and then think about what our original is doing. Anyway, just giving away answers all over the place. Go back an example. What was given to you in the table? Time and velocities. They gave us values of the first derivative, right? We're going to have to figure out how to deal with that, because that is not our goal for today. This is part of what you're going to be finishing on Friday is examples. Sorry, we're not doing that today either. Examples 1, 2, and 3, but we are going to work on them a little bit together tomorrow. Sound good? Okay. For right now, let's go ahead and go back to our notes. We might come back to some of that. Let's go back to our notes. Here we go. And figure out why on earth are we reviewing, talking about motion in a chapter that is known for starting integration? What on earth is going on such that we're starting or we're talking again about motion in a chapter known about integration? So make sure you bring your packet tomorrow. Please, please, please. We will work on those examples, just get you started a little bit. But we'll also do some more examples like the bookwork, which has to do with this page right here. This is about the section at hand, 4.1b. Packet is mostly allowing us to review. We've already talked about how to find velocity and acceleration from position, but here's the bigger dilemma. How do we find velocity and position from acceleration? We gotta go backwards, right? We're finding position and velocity from acceleration. We have to go backwards. Ah, stink! And we might not have to go backwards just once, but maybe we have to go backwards twice. What? Can you integrate and then integrate again? People who are working on homework, the one that was due today, supposedly, but you have a little grace to maybe finish it for tomorrow if you haven't yet. Remember that integration quiz. Practice, practice. Was there a question in homework that gave you a second derivative and asked you to go all the way back to the original, so you had to go back twice? Yes! Same idea here. Those of you that haven't gotten there, struggle. Hopefully you do tonight. The question, kiddos, if velocity, not velocity, I apologize. If acceleration is equal to velocity prime, then question, how do I go back to velocity? Does that make sense? How do I go back to velocity? We'll undo the derivative. How do I undo the derivative? Well, I plug the derivative into an integral. Okay. Does anybody know what I mean by a sub naught? A sub 0? Initial acceleration, but not just initial. Question, kiddos, if that's my a of t, is acceleration constant or varying? Constant. So I'm talking about a constant integration just because these formulas are simplified for constant acceleration. Now, do all motion problems and scenarios where something is moving have constant acceleration? No, thank goodness. Otherwise, we'd be crashing all over the place because our brakes would be out, right? Constant acceleration would be we never decelerate, we never stop accelerating, we never more slowly accelerate, or more quickly accelerate. That's not true. But anyway, we're using constant acceleration because that's the easiest way, but whatever acceleration is, we could integrate to go back. Just for right now, I'm saying it's constant because I can integrate a constant. I can't integrate other functions necessarily right now. Kiddos, if a sub naught is just a constant, if a sub naught is just a constant, then question, how do we integrate him? What rule are we going to use? Yeah, the one we just put in x, but hold on, it's dt. So what am I putting instead of x? Yeah, t is my independent variable. So I'm going to have a sub naught plus, nope, times t plus c. Oh, struggle. Where's my class? Where are you? Poor little baby koalas or manatees or dolphins or meerkats or whoever
Seagull.
are dying. Eagles. Seagulls.
Baby crows.
Oh my goodness, this is so random.
Baby seagulls.
You're thinking about the eagles because the little ones I hatched over Christmas? Anyway. Now, hold on. I'm not going to stop here because here's the reason why. There's something special about C. There's something special about C. If we plug in time is 0, question, what kind of velocity am I plugging or am I finding if I'm plugging in time is 0? Initial velocity. V sub naught is initial velocity, initial when time is 0. Velocity at the beginning of a situation or scenario. What does C end up being? Oh, C is the initial velocity? Yeah. So we can rewrite this equation to just be, hey, it's A sub naught times T plus V sub naught. But here's the idea, kiddos. It's not really something necessarily that I want you to memorize. I have in years past, and if this was a physics class, I probably would. But since this is calculus, I just want you to get the idea of what we're doing. Whoever acceleration is, whether he's constant or varying, whether he's just a number or whether he has a t in there, in order to find velocity, we integrate. And if they give us a clue, we plug it in to find c, right? Now, if we have this for velocity, what do we do to find position? Derive again. Because if velocity is position prime, and if I want to get back to position, I need to anti-derive. So I'm going to take that velocity function. I'm going to throw him in an integral. If velocity is position prime, to find position, I need to anti-derive yet again. Say it one more time. Nope, careful, V prime is acceleration. Does that make sense? So I can go ahead and plug velocity into my integral. I need to integrate that puppy. How do I integrate that puppy? Oh, come on, cool kids. It's A sub naught and B sub naught are just constants. What would my integral be? T is now to the power of 2, because I have power rule, right? I can bring down a 1/2 A sub naught squared. Sorry, A sub naught T squared. So T, increased by a power, divide by that. Plus, what's the derivative of any constant? No. Oh, sorry, I meant integral. What's the integral of any constant? Yeah, the coefficient or the constant times the variable plus C. But is there anything special about C again? Yeah. If we plug in when time is 0, which would be the initial who? Well, the initial, who are we talking about? Position. That cancels, C is just X sub naught. Which means I can say X of T is equal to 1/2 A sub naught T squared plus B sub naught T plus X sub naught. Or some of you physics Ians have talked about this year at some point. I'm sure you've seen this formula. Just you might have said 1/2 gravity times squared. It all comes from integration. The math is what got you the formulas that you're using in the first place. What? Go team. Formulas for what kind of situation again, though? Situation where you have a constant acceleration. But couldn't the math help you if it wasn't constant? If you knew some other equation, wouldn't you just throw him in an integral and then go from there? Yes. Okay, now how on earth are we going to use this in section 4.1b? Well, we're going to use this in order to be able to solve some examples. Now, let's go ahead and just make our forever card tomorrow. Is that cool? Because we're kind of ahead of period 1. How much time do we have? Like a minute? We're not going to go crazy. We're just peeking at an example that comes straight from our book to say, okay, wait, why is this in this section? What's given? Physixians. This will sound familiar. A ball is thrown upward with an initial velocity of 64 feet per second from an initial height of 80 feet. What? Wait a minute. But what if we were to take maybe some of our notation and say something like, oh, so v sub naught is equal to 64. And initial height, x sub naught, is equal to 80. Wait a minute. Does anybody know one other thing I really want? Oh, what's a sub naught? They don't tell us. Wait, ball, thrown. It's going to drop. What is this cool thing that acts on the earth in order to make things drop?
It's gravity.
And guess what gravity is?
9.8.
Gravity is an acceleration.
It's 9.8.
And don't worry, we're going to write down stuff like use. Don't worry. Check it out. Gravity is going to be, can you see it? It's kind of small. There we go. Gravity is going to be given to you. Cool deal? Alright guys, we're going to keep working on motion tomorrow. Thank you for hanging in there today. It's warm, so even I was tired. Happy Wednesday. I'll see you on the flip side. Bye guys.
Sucks. Like the metric system. The decimal point.